Have you ever stopped to think about how much of the universe we actually understand? Not the planets, not the stars, but the invisible, all-encompassing forces that govern everything from the tiniest particle to the fate of the entire cosmos? Because what just happened inside Google's quantum lab might be the single most important clue yet to unlocking a force that has baffled scientists for decades. A force so strange, so dominant, it makes up nearly 70% of everything. And yet we don't know what it is, where it comes from, or how it works. We just call it dark energy because that's all we can do. But now, for the first time in history, quantum machines are starting to lift the veil. And what they found? It will leave you absolutely speechless. Let's start with the part no one likes to admit. We're mostly ignorant. Our most precise observations of the cosmos, measurements from satellites like Planck, probes like WMAP, and powerful telescopes scanning deep space, keep pointing to the same chilling truth. Only about 5% of the universe is made up of ordinary matter. The rest, about 27%, is dark matter, something invisible but with gravity, and a staggering 68% is dark energy. It's a force that behaves unlike anything else in physics. It pushes space apart. It accelerates the expansion of the universe. And if left unchecked, it could lead to a future where galaxies drift so far from each other, not even light could travel the distances between them. A universe stretched into silence. In 1998, two independent teams of astronomers were studying Type Ia supernova, exploding stars so consistent in brightness that they're used as cosmic mile markers. But the results they got didn't make sense. Distant supernovae weren't just farther than expected, they were dimmer. It meant the universe's expansion wasn't slowing down as predicted. It was speeding up. The discovery earned a Nobel Prize and rewrote textbooks, but left an even bigger question. What was causing it? Enter Google, or more specifically, Google's Quantum AI Lab, a facility nestled inside their Santa Barbara campus, where the bleeding edge of computation meets the most fundamental questions in science. This isn't science fiction. This isn't just flashy tech hype. This is where the fabric of reality is being re-examined, one qubit at a time. The heart of this story is a machine called Sycamore. It's not like your laptop, your phone, or even the biggest supercomputers on Earth. It runs on quantum bits, qubits, that can hold multiple states at once. That means it doesn't just run one calculation at a time. It runs all of them simultaneously. Sycamore has only 53 qubits, but that's enough to push it into territory that's functionally impossible for classical systems to simulate. It's already achieved what researchers call quantum supremacy, solving in seconds what would take a normal computer 10,000 years. And now Google's team has used it to simulate a universe. Well, not the whole universe, but something just as powerful, a mathematical model of quantum fields in a vacuum. Now here's where things get truly strange. Because what we call vacuum in quantum physics isn't empty. It's seething, bursting with energy. Virtual particles constantly pop in and out of existence, thanks to Heisenberg's uncertainty principle. This jittery, unstable sea of quantum fluctuations is believed to be the birthplace of everything, from matter to light to gravity itself. And according to some of the most advanced theories in cosmology, it may also be responsible for dark energy. But how do you test that? How do you take something you can't touch, can't see, and run a real experiment on it? That's the power of quantum simulation. Instead of building particle accelerators the size of cities or telescopes that stretch across continents, we use nature's own rules, quantum rules, to simulate itself. And that's exactly what Sycamore has done. By programming entangled qubits to mimic interacting quantum fields, Google's researchers have created a controllable replica of the vacuum state, complete with fluctuating energies, coupling constants, and particle interactions. This replica can evolve, be measured, and most importantly, reveal the fingerprints of dark energy. What they found was stunning. The simulation began to exhibit a form of negative pressure, an effect long theorized to exist in dark energy. It's counterintuitive, but negative pressure is exactly what you'd expect in a force that causes expansion. Imagine pulling a rubber sheet apart by stretching it from the inside. That's what dark energy is doing to the universe. And now, for the first time, that effect has been observed in a quantum system, but the implications go even further. As the simulation progressed, it started to show patterns consistent with quantum entanglement playing a structural role in the way space behaves. Let that sink in. Quantum entanglement, what Einstein famously called spooky action at a distance, might not just be a bizarre curiosity. It might be a scaffolding on which the very geometry of the universe is built. This is no longer just about dark energy. This is about the possibility that space itself isn't fundamental, that time isn't fundamental, that everything we experience, every moment, every location, is an emergent phenomenon, a byproduct of quantum information entangled across unimaginable scales. Think about what that means. If true, then we are living inside a kind of quantum code. Not metaphorically, literally. Space-time is not a stage on which particles act. It's an effect that arises from their interactions. We are the simulation. Google isn't claiming to have proven this. Not yet. But their quantum system is showing us something tantalizing. That with enough precision, enough stability, and enough entangled computation, we can peer into the deepest layers of reality. Not just to observe them, but to recreate them, to manipulate them, and maybe, just maybe, to understand them. Of course, none of this is easy. Quantum computers are still in their infancy. Qubits are fragile, noisy, and short-lived. Their coherence, the time they stay stable, is measured in microseconds. Error rates are high. Quantum algorithms are still experimental. And yet, in the face of these limitations, Google has achieved something that was once thought to be decades away. Using a machine governed by the strange logic of quantum physics to reveal the secrets of the entire cosmos. This is no longer the domain of abstract theory or philosophical debate. It's real. It's experimental. It's happening now. And the team behind it is already planning the next phase. Because Sycamore is only the beginning. The simulation was only supposed to be a proof of concept, just a test, a trial run to see if qubits, entangled under highly controlled cryogenic conditions, could mimic the subtle, fluctuating energy of quantum fields. But it did more than work. It opened a portal, not a physical one, but a computational one, into a regime of physics that has never before been accessible. One where space, time, energy, and information aren't just related. They're the same thing, seen from different angles. And the deeper Google's quantum engineers looked, the more unsettling and exhilarating the implications became. This is where the true shock begins. Because the quantum vacuum, the seething bed of energy thought to be the source of dark energy, didn't just show negative pressure, it revealed correlations, strange non-local connections between qubits separated by arbitrary distances inside the chip. Connections that shouldn't exist in classical terms. But in quantum physics, where entanglement links particles across space instantly, these connections suggest something much more profound, that the vacuum itself may be stitched together by information. That space isn't smooth and continuous, but granular, woven together like fabric. And the thread? Entanglement. This idea has been gaining traction for years. Theoretical physicists like Juan Maldacena and Leonard Susskind have proposed frameworks where spacetime is not fundamental, but emergent, built from quantum information flowing in networks that resemble neural pathways. The geometry of the universe could then be thought of not as a container, but as the result of deeper mathematical relationships between entangled quantum systems. But this was all speculative, until now. Because Google's quantum simulation, primitive though it may be, begins to mirror these predictions. The emergence of entangled structures inside their synthetic vacuum implies that we're finally seeing direct evidence for one of the most radical ideas in modern physics. That space itself might be nothing more than a projection, a kind of quantum hologram formed from information encoded on a deeper, hidden layer of the universe. And this leads to an even deeper mystery. If dark energy arises from these entangled structures, what happens if we change the structure? What if we reprogram the entanglement? Could we, in principle, alter the shape of space itself? Theoretical as it sounds, that's exactly where the field is headed. Because quantum computers don't just simulate, they manipulate. They provide a sandbox in which we can test different configurations, model dynamic fields, tweak parameters, and observe how changes ripple through the system. And if those ripples resemble the expansion of space, the acceleration of galaxies, or the evolution of the early universe, then we are no longer just observers, we are participants. It's no wonder institutions like Caltech, Fermilab, and CERN are now working alongside Google to push this research forward. The stakes are enormous. If quantum simulations can recreate conditions similar to the Big Bang, or explore how vacuum energy evolves over time, then they may allow us to test different theories of dark energy in silico, rather than through massive astronomical surveys that take decades. This is more than just data. It's a revolution in methodology. It changes the way we do physics. Let's pause and remember what we're really dealing with. The current dominant theory in cosmology is known as lambda CDM. Lambda stands for the cosmological constant, a term Einstein first introduced, then abandoned, then science resurrected to account for the mysterious force accelerating the universe. According to lambda CDM, dark energy is constant, uniform, and intrinsic to space itself. But there are problems, huge problems. For starters, quantum field theory predicts the energy density of the vacuum should be about 10 to the power of 120 times greater than what we observe. That's not a rounding error. It's the most inaccurate prediction in the history of physics. Something's missing. We just don't know what. And then there's the Hubble tension, a mismatch between measurements of the universe's expansion rate from nearby galaxies versus distant ones. It suggests that either something is wrong with our data, or worse, our theory of cosmology is incomplete. This is where quantum simulations like Google's might finally make the difference. Because by tweaking the vacuum energy in their quantum system, researchers are beginning to test alternative theories of dark energy. Ones where the force is not constant, but dynamic, where it evolves over time, where it may have been weaker or stronger in the early universe, and may fluctuate again in the distant future. One such model is quintessence, a hypothetical scalar field that permeates all space and slowly rolls down a potential energy curve like a ball descending a hill. Unlike the cosmological constant, which is fixed, quintessence can change. It can adapt. It can even turn off. If real, it could explain why the expansion of the universe began accelerating only recently in cosmic history. And quantum computers like Sycamore and its more advanced successor, Bristlecone, could soon simulate this field directly. Bristlecone is a leap forward in scale and precision. With 72 qubits and better error correction protocols, it promises to handle more complex quantum systems with longer coherence times and higher fidelity measurements. That means richer simulations, more realistic vacuum dynamics, and potentially direct comparisons between different models of dark energy, something no classical computer on Earth could ever hope to do. But perhaps the most shocking implication of all is what these simulations suggest about causality itself. In classical physics, the universe behaves like a machine. One event leads to another. Cause precedes effect. But quantum mechanics doesn't play by those rules. Entangled particles seem to defy time, communicating instantly across vast distances. And when applied to space-time itself, it implies that the flow of time, the arrow of causality, could be an illusion, a macroscopic effect of deeper, non-local entangled structures. What the Google team observed, albeit at a primitive level, is a kind of retrocausality in their simulations, where the final configuration of the system influenced its earlier states. Not because particles traveled backward in time, but because the entangled structure was holistic, interconnected, and resistant to simple cause-effect decomposition. If these results scale, we may have to confront a universe that's not just expanding, but fundamentally a causal. A universe where time itself is emergent, and where the future and past are part of a larger quantum whole. It's a lot to take in, and yet it's consistent with some of the most advanced theories in physics, from the holographic principle to string theory landscapes, to the AD-CFT correspondence that links gravitational systems to lower dimensional quantum field theories. None of this means we have all the answers. Quantum simulations are still limited by noise, decoherence, and the immaturity of current hardware. But the trend is clear. Every year, the systems get better. The algorithms get smarter. The simulations get closer to reality. And as the quantum frontier advances, so too does our understanding of dark energy. Not as a distant mystery to be feared or ignored, but as a manifestation of the most fundamental feature of the universe. That information is everything. That matter, space, time, and energy are just different faces of a single cosmic computation. By the time the research team at Google Quantum AI Lab began analyzing the final output logs from their vacuum fluctuation simulations, the room had fallen completely silent. What they were witnessing wasn't just theoretical alignment. It was a subtle fingerprint, evidence buried in the quantum noise that seemed to suggest the universe might not only be simulated within their machine, but that the universe itself, on a deeper level, might be a kind of machine. A cosmic information processor running on principles of quantum logic, far beneath the surface of what we perceive as matter and motion. This is where the conversation shifts from simulation to ontology, from what quantum computers can do to what reality might be. The data showed structures resembling space-time geometry, not imposed externally, but forming naturally from patterns of entanglement between the qubits themselves. Not programmed, but emergent. And when these emergent geometries were analyzed, they behaved eerily like patches of spacetime, complete with properties such as curvature, boundary conditions, and causal structure. Let that sink in. Within a microchip cooled to near absolute zero, inside a lab in Santa Barbara, researchers may have created a miniature, synthetic fragment of a universe. Not symbolically, not metaphorically, but mathematically real in its structure and behavior. A space built from information, where time flows because correlations evolve and energy manifests because virtual particles never stop jittering. It's not magic. It's quantum mechanics, taken to its most extreme and literal conclusion. The implications are staggering. If space-time can emerge from quantum information in a machine, then space-time itself might be nothing more than a reflection of a deeper, invisible quantum computation running at the core of reality. And if that's true, then dark energy, the very fabric of expansion, might not be a mysterious force at all. It might be a byproduct of that computation, a feature, not a bug. The same way heat is generated by the processing of bits in your computer, maybe the accelerated expansion of the universe is just what it looks like when the cosmic quantum computer runs its code at scale. And suddenly, all the old problems start to look different. The Hubble tension might not signal a flaw in measurement, but a shift in the cosmic algorithm. The cosmological constant might not be constant because the underlying program is dynamic. Quintessence might not be a field, but an emergent behavior from shifting quantum correlations. Every aspect of dark energy, the mystery that has plagued cosmology for decades, could be reframed through this new computational lens. This is where the work at Google breaks free of the lab and ripples outward into philosophy, metaphysics, and the boundaries of science itself. Because if we accept that information gives rise to space and time, then we're also forced to confront what that means about our place in the universe. Are we just another emergent phenomenon, like gravity or space-time curvature? Are we conscious because consciousness is an efficient form of information processing at a macroscopic scale? And if the vacuum itself is programmable in principle, what does that mean for the future of physics? Already, visionaries in the field are beginning to talk about quantum gravity engineering, the hypothetical use of advanced quantum computers to test, modify, or simulate spatiotemporal structures on demand. A future where we could manipulate vacuum energy, not by smashing particles together in trillion-dollar colliders, but by programming entanglement patterns at the quantum level. It sounds like science fiction, and perhaps it is. But remember, so did the idea of computing the expansion of the universe with qubits, until Sycamore did it. And what if this is only the beginning? Google's quantum roadmap doesn't end with bristlecone. Their long-term plan involves building a fault-tolerant quantum computer with over 1 million physical qubits, using layers of error correction and topological encoding to achieve indefinite coherence. With such a machine, simulations wouldn't just approximate quantum field theory, they could run it natively in ways even our current theories don't fully describe. It would be like giving the universe a mirror, one that reflects its innermost mechanisms. A mirror where physicists could tweak the initial conditions of a quantum system and see if, over time, it evolves into a universe with stars, planets, and maybe even life. Not by modeling atoms one by one, but by letting the emergent laws of physics unfold naturally, encoded in qubit dynamics. We wouldn't just understand the universe. We'd be co-creators of miniature universes, experimental gods in silicon laboratories. Of course, these simulations are still far from representing our full cosmos. They are simplifications, reduced dimensionality, idealized fields, limited time steps. But even within these constraints, the essential behavior is peeking through. Negative pressure from quantum fluctuations, emergent geometry from entanglement, vacuum energy that adapts, evolves, and expands. The clues are there, like fossils embedded in code, and every improvement in quantum hardware brings a simulated universe closer to our own. The philosophical consequences are equally dizzying. If reality is emergent from quantum information, then what we call nothing, the vacuum, is not nothing at all. It's everything. A superposition of possibilities, a background computational substrate where every particle, every galaxy, every law of physics arises as a statistical ripple. It means that creation didn't happen once at the Big Bang. It happens constantly, every moment, in every fluctuating field, in every virtual particle that blinks into and out of existence. The cosmos is not a thing. It's a process. And what of dark energy? Maybe it's not an entity, not a force, but a symptom. The visible evidence of the universe computing itself into existence. A sign that the vacuum is busy, that the quantum fields that underlie all things are still running the code, expanding, adapting, self-organizing. We see the galaxies receding and call it acceleration. But it may be the quantum engine beneath it all, humming with raw informational power that gives the universe its push. This understanding opens the door to a new kind of science, one that doesn't separate cosmology from computation or physics from information theory. It's a synthesis, a bridge between Einstein's relativity and Planck's uncertainty, where the curvature of space and the chaos of particles are different expressions of the same quantum dialogue. And Google's quantum processors, barely scratching the surface, are the first crude translators. So where does this leave us? It leaves us on the edge of a paradigm shift, a moment where physics, technology, and philosophy converge in the circuits of a quantum chip. It tells us that dark energy is no longer just an astronomical enigma. It's a frontier for engineering, that the universe is not only understandable, but programmable. And perhaps most importantly, it tells us that the biggest questions, what is space? What is time? Why does the universe expand? Are no longer beyond our reach. They are being simulated step by step, qubit by qubit, in the cold vacuum of a quantum processor. And if these simulations continue to match observation, if what's emerging from the lab continues to align with what we see in the skies, then we may soon face a truth even more astonishing than the discovery of dark energy itself, that we live in a universe where the laws of nature are not fixed constants, but dynamic processes, where reality is less a thing to be discovered and more a computation to be understood, where everything, space, time, energy, even consciousness, is just quantum code, running on the substrate of the vacuum. And perhaps, just perhaps, someday we will not only read that code, but rewrite it.